our session today. And today's speaker is Professor Nikolai Ivanovich Portenko with a talk about killing coefficient of multidimensional Brownian motion, killed at heating time of membrane. Please, Nikolai Ivanovich.
Thank you. Just a moment. Slideshow. Oh, no. This is the title of my talk today.
But Nikolai Ivanovich, we haven't seen your slides.
Yeah?
Yeah.
Oh, I am sorry. And what I have to do? I have. Hello?
Hello?
Oh, share screen.
Yes, exactly.
Share screen, and then?
But it seems it does not work because we don't see your screen still.
Maybe this is share screen.
Mm-hmm. Still the same.
Still the same. Maybe this is your screen.
No, I can see you.
Okay.
But we have already seen there was a trial before the beginning of the seminar, and it was successful.
Yeah.
Oh,
now it's good. Mm-hmm.
No, slideshow.
Mm-hmm.
And okay.
Yes, now it's perfect.
Okay, this is the title of my talk today. Unfortunately, I have not yet put the finishing touches to the investigations, my investigations on this topic. Nevertheless, I hope my main idea will be formulated quite comprehensively. Okay. So let us consider some Markov processes, in phase space XB. This is Dynkin's notation, and in this notation, zeta means the lifetime of the process, or in the other words, the instant of time when the process disappears from the phase space. Okay? And the definition of the killing coefficient is as follows. K of x for x in phase space is equal to limit t to the power -1, and this probability that the process is killed, has been killed by the time t. Okay, and we should calculate this limit as t goes to 0. It turns out, however, that such a limit does not exist for many simple processes, and this definition should be modified. This modification can be realized in a way similar to that on which the notion of a diffusion process has been extended to the notion of a generalized diffusion process. In accordance with this idea, we suppose that some classes of smooth functions can be defined on X with respect to some measure dx, and assume that the limit the same, but now it is integrated over with some function phi of x, and integral is taken over all x. And now this limit must exist for any function phi of x from an appropriate class of smooth functions. The key words here are an appropriate class. If such a limit exists, that limit determines the action of some generalized function denoted by k of x on any test function phi from that class. We call this generalized function the killing coefficient of our process. Let us consider the following example. Let x of t be a one-dimensional Brownian motion filled at the heating time of the origin. The natural phase space for this process is R0. That is a real line without origin, without the origin. With the sigma algebra, B of R0 consisting of all Borelian subsets of R0. Transition probability density, GTXY, of this process with respect to the Lebesgue measure on B of R0 is given by the equality 3. Okay. Now denote by C hat of R0 the space of all real valued continuous functions phi of x defined on R0 such that the set of all those x from R0 for which absolute value of phi of x is not less than epsilon is a compact in R0 for any epsilon. It is not difficult to verify that the function defined by this integral, belongs to this class C hat of R0 if phi is from that class. It is very easy to verify this fact, and therefore we can consider the semigroup generated by this transition probability density in this space. And it is well known that the generator C hat R0 generator of that semigroup uniquely determines transition probability of such a process. Okay? And now we can calculate this probability. This integral gives us the probability that our process is not killed at the instant of time t, and 1 minus is probability that zeta is not greater than t. And this is a very simple calculation that this integral this expression is equal to this integral. This is the distribution, the function of the random variable zeta, and this distribution is well known. There are many methods for obtaining this formula. Okay, and now we can calculate this limit for any function phi from the space C hat of R0. And supposing that phi from that class is such that phi prime 0 plus and phi prime 0 minus exist, then it is a very simple calculation. You should write down this integral as sum of two integrals. One of them is taken over the left semi-axis and another over the right semi-axis. And then we use the fact that any function phi from this class can be extended to a function, a continuous function on the whole real line, and the value of such a function at the origin is 0. So we can subtract here phi of 0 and then subtract such value, and we receive this, we obtain this formula. So in this case, we have the following assertion. The appropriate class for the process xt consists of all those functions phi of x from C hat of R0 for which the limits phi prime 0 plus and phi prime 0 minus exist, and the killing coefficient k of x acts on a function phi from this class according to the following rule. So you see, k of x is the generalized function of the following type. It is like the derivative of Dirac's delta function. Okay. No. By the definition, every killing coefficient must take on only non-negative values. One can easily comprehend that in our case, we have k of phi, the action of k on a test function phi is non-negative if phi of x takes on only non-negative values for all x from R0, because such a function is extended to a function on the whole real line, and phi of 0 for this function is equal to 0, and this is a point where phi attains its minimal value. It can be not differentiable at the point at the origin, but the derivative, we supposed that the derivative phi prime of x has the limits from the left and from the right. Okay, so this action must be non-negative. And the question arises, is it possible to define the functional k of x of s? Some reasons for the negative answer to this question can be found in the article Osipchuk and Mikhail Osipchuk and myself that was published in 2018 in the journal Stochastic. Okay. Nevertheless, nevertheless, as proved in that paper, transition probability densities of Brownian motion, that is this function, and of our process, it was denoted by GTXY, are connected by the Feynman-Katz transformation. You see, this inner integral is a symbolic one because k of z is a generalized function. So this integral should be understood as the action of function k on this product as, and we consider this product as a function of z. So k must act on this product, and it is not difficult to calculate this action, and we have the following expression here. And now it turns out this expression should be integrated as a function with respect to argument tau over the interval from 0 to t, and this integral can be easily calculated, and we have this expression, and this is exactly this integral. So we have GTXY equals G0TXY minus G0, that integral. That integral is nothing else but G0TX, T, comma, minus absolute value X, comma, absolute value Y. Okay, and now I should remark that the fact that k acts on a smooth function phi means that phi 0 equals 0, and this is something like like the procedure of renormalizing of functional described, for example, in the articles by Dorogovtsev and Bakun or Alexei Rudenko. It looks like we subtract from that functional, we subtract local time, the integral of delta of x of t dt, okay? And then we have this this functional that is as if from the second floor in hierarchy of generalized functions. Okay, and now I would like to propose another way to calculate the killing coefficient for this process that does not use the explicit formula for the distribution of zeta. The previous consideration were based on the explicit formula for the killing, for the time, for the lifetime of this process. We now describe some other way for calculating the killing coefficient. That way turns out to be useful in multidimensional cases as well. Denoted by x0 of t, Brownian motion on a real line. As is well known, there exists an additive homogeneous continuous functional eta t of the process x0 of t such that its values are non-negative and the relation 13 holds true for all t and x. This functional is called the local time of x0 of t at the origin. G0, I would like to recall that this is the transition probability density of Brownian motion on the real line. For non-negative mu, we denote by g mu txy, the function defined by the relation that must be held true for all t, x, and phi from the space of all continuous bounded functions defined on the real line. Okay, this function g mu can be found out from any one of these two equations. This equation connected g mu and g0, okay? And how to derive these equations. Let us consider the following integral, the following functional of integral type of the Brownian motion, okay? And for fixed epsilon positive, G0 is a nice function. So this functional is well defined, and we can write down for this functional the equation like this, but here we will have two integrals. One integral will be with respect z instead of 0, z, and this function epsilon z0 should be. But it is evident that g0 epsilon x0 goes to delta function, Dirac's delta function, so that inner integral vanishes, and we have these two equations. The function g mu serves as transition probability density on some Markov process on R and dot to top. No. I'm sorry. And it is not difficult to calculate the lifetime of the process x mu. This is the Markov process on a real line whose transition probability density with respect to Lebesgue measure is g mu. So the distribution of lifetime of this process is given by this expression, and we can easily calculate the killing coefficient for this process. You see, we should calculate the limit of this expression. We can add and subtract this issue, this item, and because expectation of this functional is this integral, we have that the first item on the right-hand side here is the limit. It is equal to mu phi of 0. And the second one can be estimated as follows. 1/2 mu squared over t, and expectation of eta t squared can be estimated in this way as 2, this supremum and this integral, and we have just seen that this goes to mu phi of 0, so this goes to absolute value of phi of 0 as t goes, and this supremum is estimated by square root of T tau over P. So the second item here goes to 0, and we have that the killing coefficient of the process with this transition probability density is equal to mu Dirac's delta function, okay? And now we are going to pass to the limit as mu goes to plus infinity. It is evident that for fixed t, the relation e to the power minus mu at a t converges to this indicator, where zeta is the lifetime of our process, that is the Brownian motion filled at the heating time of origin. And it is not difficult to verify that this probability is equal to 0 for fixed t and any x from R0. It means that zeta has the continuous distribution function, and we know this the distribution of zeta, but I now cannot to use my notion about this distribution. But it can be established, this equality can be established from the equations, for the function, from these equations, okay? Now we have the following relation. So I know that this goes to this indicator, and with respect to measure Px, this indicator is the same as indicator of zeta is greater than t, strictly greater, and this is expectation of phi of x of t, where x of t is a Brownian motion killed at the origin, at the instant of time when it hits the origin, the Brownian motion hits the origin. So we know that g mu in weak sense goes to gtxy. And let us look at the second equation in 15. If we integrate both sides of this equality with respect to y over the whole real line, we we obtain here 1, and here minus mu integral over this interval 0t. This is 1 mu g mu tau x 0, the tau. Okay, and we have the following equality. This distribution is the limit of mu g mu integral from 0 to t mu g mu g mu tau x 0 d tau. Okay, and how to calculate mu? Limit mu g mu times g mu tau x 0. One can write down the solution as the sum. Let us apply the method of successive approximations to the equation, to first or the second equation, and define the following sequence of function g0, defined by this equality, and gk, for k equals 1, 2, and so on, gk equals this integral, and the very simple estimation show that gk, that this series is convergent, and we can, it is easily to verify that this is the solution to each one of our pair of equations. Okay? In particular, the function g mu t0y solves the equation where g0 t minus tau 0, 0, this is simply 1 over square root 2 pi t minus tau. Denote by g the operator that acts on a function phi of t in accordance with the rule. This is convolution of phi with this function g0 t minus tau 0, 0. Oh, no. Excuse me. Now, let us write down the function g mu t0y as the sum of this series. One can easily comprehend that gk g0, this is exactly is gk of t0y. Okay, and let us write down minus mu to the power k as this integral 1 over mu integral e to the power minus theta over mu minus theta to the power k over k factorial d theta. And it can be written in this way. This is exponent of the operator G, and this operator is applied to the function G as a function of this argument. Of this argument, and as a consequence of this, we have that mu G mu T0y converges as mu goes to plus infinity, converges to this integral of this operator, and this is nothing else but G, the inverse operator for G. And so we have to calculate this result of applying G minus 1 to to the function G0 of T0y. Okay? And so we have just obtained that this limit must satisfy this equation. G0T0y must be equal to the convolution of unknown function, this one, okay, with this kernel. And it is evident that the solution is exactly the density of the distribution of the random variable zeta. So we have just proved that mu times G mu T0y as mu goes to plus infinity converges to this density. Okay? No, and now we have already seen that if we multiply both sides of this equality by phi of x and integrate over all x, and if phi from our appropriate class, then the Killing coefficient can be calculated. Okay. And I would like to say that any of our pair of equations can be easily solved in the general form, and one can write down the following expression for the function g mu. This is the transition probability density of the Brownian motion killed at the heating time of the origin. Okay, and one can easily see that g mu txy goes to gtxy as mu goes to plus infinity. Here we have one can calculate, one can easily pass to the limit under the sign of integral. Okay, and all mu and the limit, this limit can be calculated from starting from this relation. Okay, and I would like to say a few words about the multidimensional case. So suppose that S is a given closed bounded hypersurface in RD with D not less than 2. And we suppose that S is of the class H 1 plus kappa for some kappa from the interval 0, 1. And let x0 be a standard Brownian motion in RD. We can define the functional of the process x0 of t that is called local time on S, and this is in Dinkin's terminology, a W functional with its characteristic given by these integrals. The inner integral is a surface integral, and these integrals are well defined because this integral can be estimated by some constant over square root of tau. And this integral exists, okay? And now we follow the way that has been just presented. We define the function g mu txy in such a way that this equality holds true for all t, x, and phi, and any measurable bounded function phi on RV. Then g mu tx y can be found out as a solution to any one of these two equations. Okay? And you see, this integral in the first equation is a simple layer potential for the Brownian motion. Here is G0, and here is the density of single layer potential. Okay, and the main property of single layer potential consists, the main property is described by the following well-known theorem. Theorem on a jump of the normal derivative of a single layer potential applied to the first equation. It gives the relation. Here, nu of x is the outer unit normal vector to S at the point x. And G nu of x plus, is the limit, the normal derivative as at the point x that is in outer region, and that point must go to some point on S from this limit must be non-tangent limit as y goes to point x on S from outside of our surface, okay? And this is the inner non-tangent limit of such a derivative as the point goes to a point on x from the inner region. Okay, so the difference between these two derivatives, limit derivatives, is equal exactly G mu. Okay, exactly this. And this is the key to calculating the killing coefficient for Brownian motion in RD that is killed at the instant of time when that process hits for the first time the surface S. Okay, but I have not. I'm not ready to discuss the final expression, because some expression for that killing coefficient, because some details are not clarified for me. Okay, so I would like to finish my today's. Thank you for being attentive.
Okay. Thank you very much for interesting talk. And maybe somebody have questions or comments, please. So, Nikolai Ivanovich, let me formulate what is the main difficult in multidimensional case?
Difficult. I think that this formula gives us the hint how to calculate the limit of mu mu as mu goes to plus infinity. But I have not comprehend something. I am not ready to discuss this.
Okay, I see. So, of course, the set of generalized functions is much more large than generalized function, which is concentrated in 1.0, the one-dimensional case. So,
yes. This function will be concentrated on S, on the hypersurface, yes.
And the variety of such function is much more large than in one-dimensional case. By the way, do we have the same description? Because in one-dimensional case, we have that all generalized functions concentrated in one point are delta function and its derivatives. That's all what we can have. So what we can say about the multidimensional case and the generalized function which is concentrated on the surface? Do we have something similar?
I think that something like this difference between the derivative, normal derivative from the outside and from inside. Okay.
I see. So still we have at least theoretical description of what can be a limit and
I do not know such a result. In one-dimensional case, we know that the generalized function concentrated at one point is
exactly
a Dirac delta function or derivatives of it. Okay? And in this case, I do not know such a result.
I see. Okay. Thank you. Thank you again for interesting talk. And for today, we finish our work. Georgi, do you know who will be the next speaker?
The next speaker will be Kirilo Kukuchinsky.
Okay, so we'll discuss equation with interaction. Okay, thanks everybody and see you next week. Bye.
Bye.
Thank you. Bye.
Thank you. Bye.
Thank you.
Thank you. Bye. Thank you. Bye.
Thank you. До побачення.
До побачення.